Without any further ado, let's get into it because we have a bit of material that we need to cover. It's a very interesting topic, a bit controversial as well. But in today's scope of our discussion, we will focus what hydraulic fracking means and how it plays a very important role um, in our energy industry. So I will quickly go through what well stimulation means because hydraulic fracking is part of well stimulation. So we need to understand what are the different aspects of well stimulation. Then we will talk about what are the goals, what are the objectives of hydraulic fracking, how it's how it paved a very pivotal role in developing the oil and gas industry, primarily in US and Canada, and what are the different design considerations and the summary. So stimulation introduction. Stimulation is actually a part of oil and gas production in which we try to increase the reservoir uh, flow capacity. We are trying to we are getting fluid on the surface. It can be a mixture of oil and gas. It could be a condensate. It could be just gas. And we are trying to improve the flow capacity. There are two or actually three ways in which we can actually improve that uh, uh, flow capacity. Number one is called wellbore cleanup. In this wellbore cleanup, we are actually not trying to inject anything into the formation. It's purely a mechanical cleanup in which you are trying to reduce debris, you are trying to clear up formation, you are trying to remove any impediments that are preventing the oil and gas to flow into the wellbore. Perforation wash is one of them, chemical treatment is one of them. You are just injecting certain chemicals. You are not injecting, you are just flushing it with chemicals so that your wellbore is cleaned up so that all your oil and gas can actually flow into the wellbore. The other is called matrix treatment, in which the certain chemicals that includes acid, primarily hydrochloric acid, and solvents which are injected into the reservoir. Now, this matrix treatment is different from fracking because this injection is done at a pressure much below the frac pressure. Now, frac pressure, or the pressure at which your formation rocks will crack open, is very important because in matrix treatment, this injection is done below that frac pressure. In matrix acidizing, what actually happens is that we are trying to clear the damage zone in the wellbore. We are trying to dissolve the carbonates. We are trying to dissolve anything that can impediment the flow of oil and gas into, or the production flow into the wellbore. If it is being impeded by anything in the matrix treatment, we are injecting solvents and acids just to dissolve that. And this injection is done being at a lower than a pressure gradient of the rock. In fracturing, which is the third type of well stimulation, this injection is done above the frac pressure. That means you are actually injecting a fluid at a very high pressure, which is much higher than the pressure gradient of the formation. The pressure gradient of the formation is actually measured in pounds per square inch. So certain different formations have their pressure gradient, and the fracturing is done at a pressure of 5,000 psi, 10,000 psi, 15,000 psi, depending what type of formation you are trying to fracture. And it is done with a certain aspects in mind. There is a certain pressure that you need to require. There is a certain type of fluid that you require, because what you are trying to achieve in fracture is to crack open that rock so that you reduce the permeability of your formation, so that the fluid can actually go into the wellbore, but also you are trying to make sure that once the pressure is relieved, those fissures or those cracks will stay open even after that. So there are two types of frac, which are acid frac and prop frac. We are going to discuss a bit of how do they work in the coming slides. This is just a quick introduction about the wellbore and the reservoir and the damage zone. So damage region is primarily a region which is not producing oil and gas in a formation. This is usually situated around the wellbore. It is damaged by different drilling conditions. It could be damaged by different type of rocks that have come up, and effectively block that region. What we want to do is that we want to create fissures that go beyond that damaged region, so they actually bypass that damaged region, uh, and get that fluid flowing through the reservoir. Uh, so this is just an introduction or indication of uh, a difference between your production or pressures after and before stimulation. So you can see that before stimulation, your pressures and the distance from the bellbore, it increases gradually until it reach to a certain production rate, while after simulation, you actually get that at a higher pressure. The higher pressure means that higher flow rate. So in the matrix simulation, what happens is it happens around 360 degree of the well bore. So you are trying to reduce in matrix simulation and fracking. The difference between them is in matrix simulation, you are trying to reduce your damage zone, while in fracking, you are not trying to reduce your damage zone, but you are actually trying to introduce frac which goes beyond the damage zone. So this is just a quick introduction. What we talked about already, hydraulic fracking is a process of using hydraulic pressure to create those artificial fractures, fracks, or cracks in the reservoir. And these grow in length, height, and width, which goes beyond the damage zone. And we do that by pumping at a very high pressure, a mixture of fluid and propellants, so that they can keep those fracks open. And why we do this? Why such an expensive method of fracking? Why we inject at such a high pressures? Primarily because we want to improve our well productivity, because there are certain wells that are not economical to produce if you don't frack them. The pressures are too low. They will quickly deplete after producing for days to months, and then it's not economical to keep them. It's not economically viable to keep them online anymore. So a lot of oil and gas producers, what they want is that they want more bang for their buck. They want more productivity from the capital expenditure that they have already done, and they do that by doing hydraulic fracking. Maximizing the NPV, which is the net positive value on the well drilling, because they want to produce more oil and gas in today's time, not 6 months down the road or 10 months down the road. Because anything that they can produce right now is the revenue for them. Increasing the hydrocarbon production, we already talked about it. Economical life of the reservoir, obviously they want to prolong the economical life of the reservoir so that it becomes a very profitable asset over the period of time. And obviously well reserves, for a publicly traded company, declaring their well reserves is very important, because that's how they will be evaluated on the stock market. What are the secondary objectives? Some of them is delaying the onset of water production. So you are primarily fracking the zones that are producing oil and gas. So it reduces the water cut, it reduces the water production from the well, and it also increases the drawdown, or how long you can draw down that well over the period of time. The other aspect is controlling the sand formation. Sand is one of the aspects that actually is very detrimental in oil and gas production. It actually reduces your oil and gas productivity. It's one of the things that you want to produce as less as possible. Fracking is one of the means of doing that. And then part of welcome. So it's very important in conventional reservoirs. It's super important in unconventional reservoirs, because unconventional reservoirs inherently are very difficult to produce. Since they are difficult to produce, they are economically not very viable. And to make them economically viable, hydraulic fracking is one of the key ingredients of the whole equation. Because by hydraulically fracking, it permanently alters the reservoir and makes it more producing and less permeable. More permeable, sorry. So as I mentioned earlier, in fracking, the frac fluid is actually introduced at a pressure which is higher than the formation pressure. The fracture will extend beyond the damaged bore of well area. As I mentioned earlier, in metric stimulation and the hydraulic fracking, the difference is that in metric stimulation, you are trying to repair the damage zone, zone which is not letting you produce. In the hydraulic fracking, you are actually going beyond that. And you can see that you are actually introducing a crack in which the fracture half length, which is a technical term we use in hydraulic fracking, is more than it goes beyond the damage zone. And it actually extends beyond the wellbore area. And it actually improves your viability. It actually lets you produce at a very quick time frame. Why do we frack? And there are two aspects of why do we frack. Why do we frack in high permeability formations, and why do we frack in low permeability formations? In the high permeability formations, frack is primarily done to increase production and to accelerate the recovery of assets or reserves. And this could be very much applicable to mature reservoirs that have been producing for many number of years. Now the field is towards the tail end of its life. You want to increase production. You want to get more bang for your buck. The way you can increase production is by doing fracking. So you you do the intervention, and you actually frack the reservoir and let it produce, and that actually extends your field life. You bypass your formation damage. We actually saw that the frac half length is actually more than the formation damage, and for sand control as well. So you are trying to frac zones which are more producing condensate, oil and gas, and less producing sand. Similarly, maximizing frac conductivity and width by achieving tip screen out. Now, tip screen out, as if I go back to my previous slide, tip screen out is a concept in which it's very critical, because it's very critical to the success of a frac. If you can see a frac, you can see that there is a tip at the end of the frac. What tip screen out means is that you want to make sure that you made this crack happen by applying pressure. Now you want to make sure that stays open when the pressure is relieved. You do that by applying certain propellants, by applying sand. Sand is very critical in fracking, because frac sand, which is of a certain mesh, it can be 100 mesh, 200 mesh, or a 300 mesh sand, and it will ensure that the fracture will stay open even when the pressure is relieved. So we want to make sure that this fracks, that very expensive fracking that we are doing, these fracks will stay conductive even after the pressure is unapplied, and it will stay open for the certain period of time. And we want to make sure that the tip won't collapse once the pressure is gone. Why do we frack in the low permeability reservoirs? Now, in the high permeability reservoirs, it helps in production. It helps in extending the life of the reservoir. In low permeability formations, it is kind of a necessity, because you can't produce them if you don't frack them. In the low permeability formations, for example, shale gas. Shale gas is a formation that actually do not extend vertically; it extends horizontally. So for the shale oil and gas production, primarily in US and in other parts of the world, there were two things that actually happened to make it happen. The first one was hydraulic fracking, and the other one was horizontal drilling. And the picture which you see on your on the top right hand side is exactly showing the two things. You are actually seeing horizontally drilled well, and you are actually also seeing a frac. So what actually happens is that since the shale actually extends vertically rather than horizontally, so you actually drill a well vertically, which will actually intersect all of that shale formation, and then you start fracking them, and you actually frack one zone, and then you will frack second zone and third zone, and the number of zones will depend upon how extended your shale formation is. Essentially, what we are trying to do is that by intersecting this whole shale formation through horizontal drilling, we are trying to access the whole formation, and also by fracking, we are trying to make sure that we make it more permeable so that oil and gas can actually flow. So as I mentioned earlier, in the low permeability formations like shale and low permeability carbonate, this is actually a necessity. You cannot make them produce without actually a fracture treatment. So you have to do it to produce at economical rate. And as I mentioned earlier, through horizontal drilling and through fracking multi-stage, you are maximizing your stage contact. So it would be critical to extend the life of the reservoir. And then multi-stage treatment, as I mentioned earlier, this is not a single frac. Single fracs are more applicable on high permeability formations, which we discussed earlier, mature formations, in which you just frac single zone. A single zone is extended vertically, so you will be able to produce it in one stage frac. Um, since in the low permeability formations, you have to do multi-stage frac because your zone is extended horizontally. So you frac one zone, and then actually you start plugging it, and you start fracking the lower zone first, and then you will start fracking as you go uh, towards what we call uh, the toe of the well. After that, there is no frac. The fracking is usually done in the horizontal part of them. So the question, one of the things which we discussed is that it increases production and it increases the time. And this is the graph which has been taken from multiple different data points across different fields, and it will show you that how a well stimulation actually works. So this is a well which is producing before stimulation. You can see that it actually produced around close to 320 barrels of oil equivalent, and over the period of around 24, around 30 months, it actually drew down to a point where it was actually uh, hitting its economical limit. That means after this, if it goes any point below this line, this horizontal line over here, it will not be economically producing anymore. That means the amount of OPEX that will be spending on this well is more than what it is actually producing. So well stimulation comes in. This well stimulation could be a metric stimulation, it could be fracking. And once the well stimulation is done, you can see how the flow rate is now after the stimulation is completed. The well starts producing at 520 barrels of oil equivalent per day, and it draws down over the period of, it goes all the way, it extends all the way towards 90 months. So you can see that compared to this small portion of well producing pre-stimulation and post-stimulation, you can see what is the difference between the economical length of the of the well life. So this is a very important graph which shows you that how important it is for us to do hydraulic fracking in certain wells and certain formations. Usually when we do the fracking, it is actually done on both sides of 360-degree of the well. And the two zones which are extended once the fracking is done are called fracture wings. And you can see that the productive sand, the two fracture wings that we see in this particular picture are extended primarily in the productive sand, which was your production zone or pay zone, and they are limited between the two barrier zones. This is just a quick overview of what a typical frac spread would look like. Frac spread is a very technical term that we use when we are describing a frac on a location. Usually we have sand, which is also a propant, in a big silos. Then we have fluid in big tanks. This is primarily your water or produced water. And then you have blender. The blender actually takes fluid and sand and blends them together into a certain slurry. And that slurry is actually pumped into a pumper. And the purpose of pumper is to actually take it at a low pressure from blender and then pump it at a very high pressure. This could be a 5,000 psi frac, 10,000 psi, or 15,000 psi, depending on the frac gradient of the or pressure gradient of the formation. And then at a very high pressure, they are injected through a fluid delivery system, which we are going to talk about in coming slides, into the wellhead and into the casing. And then you can see over here that this is your pay zone over here, and then your propant is pushed to keep the fissures open, while the fracking fluid will extend to make sure that the pay zone intersects very well with your frac zone. Composition of the frac fluid. So composition of the frac fluid is very critical, and it differs from frac to frac. No one frac is same. Uh, and this is primarily done based on how much sand do you want, what kind of a sand size or mesh size do you want for sand, and what kind of other chemicals you would require. Primarily, you can see that water and sand constitutes 99%, 99.5% of the frac fluid. Out of that 0.5, in that 0.5, it's surfactants. We have friction reducers. Friction reducers are primarily chemicals that will reduce the friction of sand within the frac fluid delivery system. And the reason for that is that the frac fluid delivery system is very susceptible to erosion because you have sand, which is very abrasive pumping through this iron and wellhead and those casing. And we want to reduce its friction with all the metallic parts. We want to reduce it because otherwise it will introduce a lot of erosion in the frac fluid delivery system. So friction reducers are primarily there to reduce that friction. We have acid. Acid is primarily to dissolve carbonates and other things which are impeding the flow. We have corrosion inhibitors, crosslinkers. We have pH adjusting agents because they are microbes downhole that we want to, which we don't want to disturb. So pH adjusting agent is there to make sure that the pH of the water and sand mixture, or the slurry, what we call it, remains to a certain level. And then we have scale inhibitors and gelling agents. This is usually a very generic mix of frac fluid delivery system. It does not hold true for any particular frac, but it gives you an idea. This is just an animated version of what I showed you earlier. We have sand storage units over here. We have frac storage units. The water is actually kept in a big pond, and then the blenders will blend, make a slurry. The slurry is then pumped into the pumpers. The pumper will pump it through a frac missile that we are going to discuss in the coming slide, and onto the wellhead and into the wellbore. So types of, so we discussed about different things on this thing. In my coming slides, I will show you some of the real life examples of all of these different subsystems of fracking, frac spread. Mixers are primarily, they are blenders. What they do is that they will take the chemicals and everything, sand, water, produce water, from all these resources, all these sources, and then they will blend them into a certain slurry. All of it is actually skid mounted, which is actually pulled by a semi, so it is very mobile and it moves from pad to pad very quickly. The rig up and rig down times are usually very quick. We have Haber unions, which will connect all the piping, and then this blender will be actually connected with the pumper. This is another type of what we call a pod. It's a single delivery system in which fully automatic process control is used for mixing of propellant, liquid, and dry additives from the control vehicle. This is another type of a blender. This one which you see over here is a skid mounted. It can be used on an offshore application, and the one which you see on the right hand side is more for the onshore applications. This is what a typical frac spread would look like. You have your blenders over here. Then you have your storage tanks over here. These are all the high pressure pumpers, which are actually pumping the slurry into the frac missile. What a frac pump actually consists of. Frac pump is actually made of three basic components. You have your prime mover, which is engine. This could be a diesel generated engine. However, the industry is slowly now moving towards the electrically operated frac pumps. Then between the frac pump and engine, you have your transmission, and then you have your XXX or quantiplex pumps. These are high pressure reciprocating positive displacement pumps, which will take the fluid from the bed blender and then pump it at a very high pressure into the formation. This is an older version of a frac pumper. This is with a it's only 1200 horsepower, while the one which you see over here is more than 2000 horsepower. Uh, so this 1200 horsepower is primarily done for low pressure fracs or for the more conventional fracs. Then you have your sand feeders. These are big truck mounted silos, which will feed sand to the blenders. And they actually serve as a temporary sand storage facility. And they actually can pump sand up to close to 18,000 cubes per minute. Um, they actually come in two sizes. One actually can hold 2,500 cubic feet of sand, and the other one can hold 4,000 cubic feet of sand. And then you have your data vans. So data van is actually a cab mounted on a chassis with all your telemetry and your electronic inputs, your pressure inputs, your pressure transducers are all connected to your data vans. And this is an older picture, but you can see what a data van would look like inside. You have your operations control center, your monitoring system, and you have an operator that is monitoring your pump's performance and also making sure that certain pressures are met while we are pumping it through the wellhead. And then sometimes you have client in the data van as well, just witnessing the frac. Frac missile, this is a term which I've used quite often. So all the pumpers, so you have frac pumps on top and bottom, all of them actually are connected through, they can be either connected to what we call iron, which is nothing except a series of pipes into the frac missile. This is a large monobore missile. What actually happens is that it will take inputs from all the pumps and commingle them into a single flow over here. This single monobore blower missile is actually could be all the way to 7-inch of nominal pipe diameter, connected through the API 6A flanges. And it is just to make sure that all pumps are actually pumping into a single frac missile, and from here it will be pumped into the wellhead. But before the wellhead, it will go to the manifold first, and then it will go to the wellhead. What you see over here is actually a bit of advancement in the technology. These pumps used to be connected to the frac missile through treating iron or the iron as what we call it. Now they are actually connected through a flexible hoses. This could be a 3-inch hose or a 4-inch hose. Sorry, 2-inch hose all the way to 3-inch hose, just to ensure that the rig up is actually done in a quicker manner without introducing a lot of downtime in between. This is just a example of you can see the flexible hoses over here. This is the fluid end of the frac truck. From here, the flexible hose is actually connected to the frac missile. Just a couple of nice shiny pictures of the equipments on location. You can see frac pumps, you can see pods, you can see blenders, and you can also see a frac missile on a big flatbed being pulled by a semi. They work in different type of onshore conditions. We could be working in deserts, they could be working in snowy Arctic, very diverse set of equipment, very highly reliable. They have to be very highly reliable because they are pumping at a very high pressure for very extended periods of time. So a lot of effort is actually done in the maintenance and reliability of this equipment. This is actually a picture of a frac spread. I will quickly change it to. So we have our frac tanks, we have our pods or blenders over here. These are all connected to the frac missile, which is a high pressure manifold. You have pumps, which are actually parked at an angle. And then you have these red lines are actually sensor cables. These sensor cables are pressure and temperature transducers. that are connected through different areas of the frac spread. They are connected with the pumps, they are connected with the blender, they are connected with the PCM, and all of that data is actually going into the data van. From data van, we are actually controlling, and we are giving uh, control commands about closing certain manifolds, opening certain valves, and things like that. That's where our wellhead is. We are going to discuss a wellhead or a frac wellhead because it's a piece of equipment that is a feat in itself, um, and all of it. So you can see the quantum of frac spread. You can see that even for fracking one well or a series of wells, which are actually called a pad of wells, it takes huge amount of equipment, a lot of people, um, a lot of technology to make it happen. A frac fluid delivery system. So frac fluid delivery system is to ensure that the slurry, which is your propellant, your sand, your water, your chemicals, are actually delivered to the wellbore in a very effective manner without any exposure to the environment, providing barrier to the environment, making sure none of these chemicals actually see out in the open, are open to the elements, making sure that the pressure is contained is in a proper manner, in a regulatory fashion. So you have conventional factory. In conventional factory, you have certain uh, amount of valves that you need to have to ensure that dual barrier is maintained. So whenever we have wellbore exposure, there's a concept which is called dual barrier, in which we are trying to ensure that at least two barriers are present all the time uh, before your wellbore fluid is actually exposed to the surface. Because once it is exposed, it's an uncontrolled exposure, right? Um, so we want to minimize it. We want to eliminate that exposure. So two barrier policy is always in effect. So in a conventional factory, you have your lower master valve, which acts as your primary control valve of the frac fluid going into the going into the wellbore or the produced fluid that will be produced during the float back operation. So you have your lower master valve, you have your upper master valve, your flow cross. This is your flow cross. This is where your frac fluid will come and tie in. Frac fluid hose will come and tie in. Then you have your wing valves, uh, uh, and then you have your swab valve and your upper swab valve. The dual swab valve. Sometimes we have just a single swab valve. Sometimes we have a dual swab valve. In this particular conventional factory, your flow cross is actually not connected to your frac fluid delivery system. Actually, your buffalo head, which is right over here, is actually connected to the frac fluid delivery system. And then in the composite factory, you can see it is much more shorter. We actually eliminate one of the swab valve, and the buffalo head is still there, and your frac fluid delivery system will come and tie in. Now, comparing this composite factory with this factory, one of the things which you will see is that this buffalo head is actually eliminated, and you have your flow cross over here, which is different from the cross over here, because over here you have a Haber union where you can come and connect your flange connection, where you can come and connect your flexible hose or your monoline uh, for the frac fluid delivery system. Um, Conventional factory, the the eventual configuration of the valves depend upon the customer choice. Sometimes the customer has dual swab valves. Swab valves are the two top valves over here. Sometimes we have single swab valves, and we have different type of pump down and flow crosses. Um, but two things never change. You always have a lower master valve, which is a primary control valve, and then you have your upper master valve, which is usually closed during the fracs. When you are fracking different wells, you can see over multiple wells over here. This is called a pad of well. It would be a pad of 5 or 6 or 10. I have seen pads of 16 wells as well. And all of these are horizontally drilled, so they will be accessing different pay zones. These conventional factories usually come up all the way up to 20,000 psi. More commonly we use 10,000 and 15,000 psi for the unconventionals, 5,000 psi for more conventional fracs. Most of these valves are hand wheel operated valves. Some of these are are hydraulically actuated as well. And we have electrical actuation options available as well. Um, Usually in a frac stack, you will have some of the valves which will be hydraulically actuated, because hydraulically actuated valve can be operated remotely. That means it can be operated from a certain distance through use of an accumulator. It sometimes act as a ESD or emergency shutdown valve. As I mentioned earlier, that we have this high pressure of sand and water at a very high flow rates, all the way up to 18 cubes per minute, um, going through the frac fluid delivery system. It takes a lot of toll on the equipment. It damages the equipment due to erosion. Uh, Sometimes we have corrosion problems as well. Sometimes we have these high viscosity friction reducer, which are part of the frac fluid interacting with the different components, with the grease in the valve, and having a degrading effect. So frac valves and reliability of the frac valves, these are the valves in the frac stack, is very important, because these are the valves which are providing you the barrier, preventing the wellbore fluid exposing it to the surface or having an uncontrolled exposure. So a lot of emphasis is done in the design and development of these valves, so that we make sure that we have more uptime on the locations, we reduce the maintenance cycles, we have erosion and corrosion protections, and while reducing the non-productive time, or NPT, and the related cost. Because you see, the quantum of a frac spread is quite high. The stakes are very high. These are millions of dollars of fracs that are happening. So reliability of the equipment is very important, because if the reliability is not there, the customer is going to incur additional cost in terms of rentals, in terms of having those pumps around. So reliability is super important. In the frac stack, we have different type of valves which are part of it. But one of the things about the frac is that all of these are gate valves, uh, or these are gate type of valves. So they have a slab type of gate with metal to metal seal. Um, we have seats which are corrosion made of CRA alloys. Uh, we are trying to make sure that we have through bore access through the frac valves, and then we have two ports for flushing and greasing through the valve cavity, to ensure that we are constantly pumping that grease to make sure that it does not go into the critical parts of the cavities in the valve, and have that detrimental effect, in which the valve can actually leak and have an exposure of the wellbore fluid or the frac fluid to the surface. So these valves are actually governed by API 6A, which is the API standard for the gate valves that are used in the oil and gas applications. We have DA2, which is direct action 2 type valves, which are hydraulically operated valves, and then we have hand wheel operated valves. Both serves their very important purpose, and they are rated to 15,000 psi uh, uh, working pressure, and the test pressure is actually rated to the 22,500 psi to ensure that you are actually testing the equipment within the operating envelopes. This is just different type of fracs. So different type of fracs actually do different type of uh, um, purposes. You have a frac over here, which is actually connecting the lenticular reservoirs. They're called lenticular reservoirs because they are in a shape of a lens. In this particular one, you have fracking to make sure that all of these different tiny lenticular reservoirs, not tiny actually, they're quite big, tiny on the screen, are actually connected with each other, so that you can actually have a single wellbore, and it can produce through all of these lenticular reservoirs. You have naturally fissured systems, so you have subparallel fissures over here and orthogonal fissures over here, and one single frac can actually connect all of them. And then you have laminated formations as well, which is entirely different aspect of a very important aspect of the fracking, in which you actually combine the acid treatment with the fracking, so that you can actually you can actually produce through the laminated formations. And then obviously the reduction in the sand production, as I mentioned earlier, that produced sand is something which we don't want. So by fracking, we actually can reduce the well drawdown in terms of sand production. I will quickly go through this in the low permeability formations. By low permeability, that means that they are not very helpful in producing of oil and gas. So we require deep penetrating fractures. That means it go very deep. The fracture half length is more it extends greater into the low permeability formations, and then we use acids and propellants to keep them open. This is part of a low permeability formation. You can see that this is flow rate versus time. You can see that over with no stimulation, the well will actually draw down quickly over the period of time. With the stimulation, it will take a long time, and then you have higher flow rates as well. And then the second graph is the cumulative production. That means your production versus time. In terms of no stimulation, you can see that you won't be able to get a lot of production, while in case of stimulation, you will be able to improve your ultimate recovery. And then high permeability formations, then in high permeability formations, you actually have all the conditions to produce at a certain level, but you want to have high conductivity ratios. That means you want to draw down quickly, and you want to extend beyond the near wellbore damage. So you require highly conductive and short fracks. So it could be only some amount of stages, not multi-stage like in low permeability formations, but short stages, low pressures to make it highly conductive. And this is just an example of the same thing, flow rate versus time over the period of time. Higher flow rates, same thing over the period, but you will be able to draw it down quickly. While in case of no stimulation, you will be able to draw it over the larger period of time. But now with the stimulation, you want to get your higher flow rate up on the onset, and then you want to draw it down quickly and be done with it. And similarly, cumulative production versus time. Time to your ultimate recovery, you still, in case of stimulation and non-stimulation, still able to, in terms of your ultimate recovery, you will be able to hit your ultimate recovery in both cases. However, with the stimulation, you will be able to do it quickly in a very shorter period of time, while in case of non-stimulation, you will be able to extend it over the period of time. Design considerations. I won't go into a lot of details over here because rock mechanics actually play a very important role in your frac design. The questions that you want to ask over here is that where do you want to grow frac, which stages, how many stages you want to do, which zones you want to do, what is the geometry, what type of reservoir it is it a lenticular reservoir it is, or if it's something else, and if it's a shale, if it's a low permeable carbonates, things like that. You want to make sure that there is no unwanted water zone above and below below your frac zone or a pay zone or a gas cap, because they can actually, if there is a water zone, you can actually frac a water zone. In that case, rather than producing oil, you will be producing water more. And then how big of an impact of frac to production. Frac is a very expensive activity. You want to make sure that your payback time period, your return of investment makes sense. And then also how sensitive the formation is to the water, and is there a good bonding behind the casing. And behind the casing, we have cement, and we want to make sure that there is a good bonding over there, because if there is not a good bonding over there, there will be a secondary flow path above the packer due to channeling behind the casing. So you will have flow behind your casing, which you don't want. Apart from that, the couple of things that I want to conclude my presentation on is that hydraulic fracking and horizontal drilling were two key activities that resulted in the shale boom in US and Canada. we were able to access reservoirs that were previously deemed inaccessible in a way they were not considered economically viable to produce. And with this shale boom, we have managed to get energy, productivity, resilience in the world, which